Okay, so the reason I skipped over double between subjects is because out of the 3 we have left for interactions, doubly repeated are probably the harder ones. We have 2 repeated measures because it requires you to do this extra weird step after you melt the data. So what I've been trying to add as we go is sort of new to this section, notes. Make this a little bigger. We covered last week that with a repeated measures design, you have to screen the data in line format because we want to account for the fact that person 1 is person 1 the entire time. But when I melt the data, what will happen is they'll make me 1 IV column and 1 DV column, which is fine if I have 1 IV. Now I'm going to have 2 IVs, so I'm going to have to create myself some new columns. And I found an easier way to do this than what we did last year. So I'm going to create myself 2 new columns, and we'll talk about how do I do that here in a minute. It is very tempting to treat this as 1 IV, but then you will miss the fact that there's an interaction. So we have to have 2 IVs. And we've talked about this before, but I want to go over it again. So specifically today, we're going to do some data for my lab. And so what we did is we gave people word pairs that are related to each other associatively. So association means I think about it in like terms of context, not semantics. So they don't mean the same thing, they're associated. Like peanut butter, not semantically related. Peanuts are not butter, but used a lot in context. So an example, my favorite example is cheddar into cheese. Yeah, I use this example a lot. Cheese. So if I say cheddar, how many people out of 100 would say cheese is their next word? It's a lot of people. This is like Family Feud in reverse. I give you the words and you're guessing the numbers. So this is like 80%. If I say cheese, how many people out of 100 would say cheddar? It's only like 10. So it's different depending on which way you give them the question. So framing matters. So what we would do is we took word pairs that were low or high relations forward, and then low or high relations backwards, and created a 2x2 repeated measures. So they saw all 4 of these types of words. I mean, they didn't know that's what was going on. But what we're really interested in is what happens with backward strength. I'm asking you to judge forwards. Is there an influence of backwards? And there is. And so what I want to do is analyze the interaction. So I can't treat this as one variable. Where's the hair this? Where's the hair? But what ANOVA is going to do is it's going to analyze just FSG all by itself. So it's going to give me, so I'm here on main effects and interactions. It's going to give me a main effect of forward strength. I don't really care about this so much, if it's significant in this particular example, because they should be rating low pairs as low and high pairs as high. So I expect that to be different. So for backward strength, it's also going to give me a main effect. So main effects are on levels. So really there shouldn't be any difference between low and high backward strength because I've told them not to think about that. Ignore this. That doesn't work, by the way. 8 experiments later. What I'm really interested in is the interaction. So interactions are about conditions. So there are differences in the condition means in here. So when I have low, 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 high, high, low, high, high. So those 4 are different. But I have to account for the fact that it's structured like this. So if I treated this as one large IV, it would ignore the structure. And what I want to do is say, well, there's something due to this and there's something due to that, but this interaction is what we're really interested in. So I want to look at ignoring these 2 issues. Let's look at the interaction. You can think about interactions in 2 ways. You can talk about them being just as the little means are different. So is low, low different from low, high? But especially because of the example we're going to do today, my question is the pattern different? Okay, this is their rating on it. Low to high. So this is low backer strength. This is sort of the picture we're going to get. So yes, low here and high here are probably going to be different. High here and high here are probably going to be different. Right? So we would say that these things are not equal. And that would be the interaction. It would be that the little condition means are different. But if you sort of zoom out, the real issue is that the pattern is different. So the difference here is, I think, is 6 points. The difference here is 13 points. So it's twice as much, or it might be 16 points. So we're trying to really figure out if the patterns of data are different across conditions. So it's not just, hey, these two little means are different, life is great. It's that the pattern between the different rows is different, which is a lot of difference at once, I know. But in the post hoc section, we'll get more into, okay, what does that mean, the pattern is different? When we get there, we'll talk about across or down, but I'm going to hold on to that thought. So we'll come back to this idea. Now, since I'm going to get more than one F-test, because I have two variables, so I get more F-tests, I kind of made a chart, because I love charts, of what you would do specifically to double repeated measures. Bless you. So if there are more than two levels. So in this particular case, we only have two levels. So this isn't true. But if there are more than two levels, and your main effect is significant, so one of the IVs is significant, the follow-up would be dependent T with Bonferroni, which is what we did last week. Okay. Same thing for the main effect here, because this is double repeated measures, so they're all dependent T. If there are only two levels, though, you don't run anything. So big star here. This is another question I like to ask people. If there are only two levels, don't run a t-test, for God's sakes. Because ANOVA and T are the same thing if you only have two. You've already run the t-test. You just interpret the mean. Look at them. This one's bigger than that one. So if there are only two levels, you just interpret. There's no post hoc test. Because remember, for t-test, there was not like t-test and then a t-test. It was just T, because there's only two. The only reason we do post hoc tests is if we have three or more. With the interaction, though, if it's significant, it doesn't matter how many levels there are, because we're talking about condition means. We're going to have to split the data in half. So, redraw my little square here. If I have an interaction between low and high, or I'm sorry, FSG and BSG, there's not a good way in R to just be like, just compare these two to each other, and these two to each other. What you have to do is create yourself two little new mini data sets. So I've got to have a low data set and a high data set, and then you can tell it to compare. So you will split one of your variables. And you can split either way. We'll come back to that. That's the across or down part.
That's only if you have two.
Two
Levels. You split like that.
No, if it's the interaction is significant, you always have to split somehow. Because there will always be multiple levels for one of them.
Right.
Yeah. That's just a practical thing. Like, I can't make R just do just these two and just these two without splitting it. The tricky part comes in, like, let's say you want to split and have multiple. You have a 3x4. That was the smallest thing we did last year. Not going there yet. We're just going to split right now. If the interaction is significant, most people will ignore the main effects if they are significant. Why? One, that saves you from running a bunch of tests. So let's say you have a 3x3 design. We're doing a simple one because that helps. I think if you can sort of ease into it, especially on a Monday. So let's say I have a 3x3 instead. Oh man, what was that one from last year? They were testing water beer and wine, and then they were giving people negative ads, neutral ads, and positive TV ads to try to get people to stop drinking, driving, or something. I don't know how you make it positive, but anyway. So it's a 3x3, which means we have 9 conditions. If I was to want to compare these on just the main effects, okay, so I've got negative to neutral, negative to positive, positive to neutral. That's 3 tests. Same here. Water to beer, water to wine, beer to wine, 3 tests. So this is pairwise. This is like making that little table box thing that we've been making. Then when you hit the interaction, it all goes to hell. Right? It's 3 for each row. 1 to 2. 1 to 3. 2 to 3. Same thing. Shrink, shrink, shrink. So I could possibly run, math, 15 tests. That's a lot. So remember, if I run a lot of tests, I increase my type 1 error. Even if we're controlling, 15 tests is a lot. Like, why? So what I could do is just do the interaction and ignore the main effects. And that way it would only be 9. That's less, at least. And then it'll save me some time and energy and type 1 error issues. What's the other thing? So if the interaction is significant, why interpret the main effects? So the point of an interaction is that this variable and this variable have different effects for each other. So if I have both variables at once, each person's reacting differently. So why would I take one variable at a time? If the purpose is to look at both of them, why look at one of them? That's kind of my theory on it. Also, I'm lazy and I don't want to run 15 tests. So you'll see, and when you see write-ups for people, they might say the main effect is significant, but we're ignoring it because of the interaction. That's pretty common. Okay, so I kind of explained the study here, but we've got 4 conditions to make this simple, and 2 IVs, FSG and BSG, and they rated each word pair type. So we're trying to look at the structure for memory. That's what's going on. Now, power, my God, it's so tiny. It's so tiny. Power for repeated measures ANOVA, singles or doubles, is the same. So this is actually exactly what we did last week. So under test family, you click F test. It's ANOVA repeated within, because everything is repeated. So it's repeated, repeated. Here's the part that's going to change. What did I say to do for this example? Let's do a small effect size. So click determine. Direct, and then small is 0.01. Calculate transfer to main. Okay, so that changed the effect size F to 0.10. Now, on the homework, you do have to do one of these, and it says take a screenshot or include all the little number typey things. You would prefer a screenshot, right, Rachel? Yeah. If you don't know how to screenshot, we'll show you, because if you have an answer that is very different than ours and we have no idea of telling how you got it, you're going to get no points for it. But if you have a screenshot and it's clear you've just mistyped one number, you'll get points. Okay, that aside. So, effect size F, alpha is always 0.05, power is 0.8, because it's 1 minus beta. The number of groups, that is not the mouse for this computer. Try again. Number of groups is number of IVs, and then the number of measurements is levels or conditions. So I got 2 IVs and 4 conditions. And then we talked a lot about that whole correlation thing last time, but let's assume that the correlation between these is 0.9. Here. That might be kind of high, but it's pretty high. I'm going to leave epsilon as 1. So you should get, if you've typed everything in the same way, 30 people. I have 158, so I'm good. Okay. So with I wrote large effect size. That should say small right there. Sorry. I don't know why it's exclamation point. Yeah, so that should say small effect size, because that's what we did here. Okay. I'm going to leave power open, because we're going to come back to it. Okay, so particular to this analysis, if you click on master here, you'll see that it has a bunch of extra columns in it, because we're going to use this data set again for a different example. So the very first thing I'm going to do is drop all the extra crap I don't need. So FSG low, BSG low, you'll see how each condition gets its own column. Okay. This is wide format. Each person's a unique snowflake, yeah. They get their own row. And that's how we want a data screen, because it'll account for the fact that each person is their own person. But I want to get rid of these two columns and my group number, because we're not using those data points right now. So this right here is just a note. This is why we're doing this. And I already have a subject number, so I'm going to keep using it. All right. Now most of this is the same, so I'm going to mostly say an R over here, but let me know if I skip something in the notes. For accuracy, you're still going to use the summary command. They were told to rate from 0 to 100, so nothing should be below 0, and they're not. Nothing should be over 100. Ignoring subject, that's not a DD column. They're all less than 100, so I don't appear to have any issues with accuracy. Yeah, so be sure you ignore subject. It's going to go over 100 because I have more than 100 subjects. With summary, I don't have any missing data. And the reason we're kind of skipping missing data, I'm not really going over it a whole bunch, is if I have missing data, I have what, 4 columns? That's 25% automatically. So they would get excluded. So mostly missing data is a non sequitur right now. It's like my favorite phrase today. I've said it like 100 times. I have to stop. It's not a thing. Okay. So even if there was missing data, it would be too much. All right. In repeated measures, this is wide format, and that is an old picture. I think you guys already know that it was late when I did this. Why? I said sound off. This computer. Something about connecting it to this monitor. It's like, whatever, I do all the sound I want. All right. Anyway, so we're in wide format. So we get to use ANOVA, but don't screen subject number. They don't have any control over that. So here we are. So all I've done here is throughout this section, I'm just dropping the subject number, which is similar to what we did in data screening. We were dropping categorical columns. So just kind of ignoring that right now. So my Mahalanobos, my cutoff with 4 columns as my DV. Not my DV, sorry. 4 columns as my degrees of freedom. Cutoff score is 18. And so you should get 1 outlier. Yes. And the outlier actually, believe it or not, is a person that did the experiment correctly. Like most people are really bad at this task. They were actually very good at it, and that's why they're the outlier. So for the real analysis, we left them in. But right now we're going to exclude them. So you'll see that our no-out data set has 1 less person. Okay. So false here means that they're an outlier, and that should match what happens up here with the number of observations here. So if you have 10 outliers and it only drops 2 people, something's not right. All right, blah, blah, blah. So additivity, this is the exact same typing here. I cut and pasted it. Because the idea, so this is really wordy, even though we've gone over it once, is that later in life, if you're like, wait, I need double repeated measures, you have all of it still spelled out. We have to check for correlations, and we just don't want them to be too high. But too high, remember here, the rule is that it can't be 1. Okay. So we're going to look at our symbols for numbers chart, and we ignore these. That's it correlated with itself. And we're looking at these. So they are correlated. Oops. but not too bad. And then I can look at the corals here, and I overestimated for power, right? So I got 6.2 is actually my highest one. So when I did that, I actually included a check yourself here and make sure you understand what's going on. So for power, if I change that to 0.62, so this will show you how much the correlation matters. We went from 30 people to 100 people. So you want it to be correlated. Because it's the same person over and over again. The less correlation, the less power, and more people you need. So don't overestimate correlations is the point of that demo. Because then you will underestimate subjects. It's always better to overestimate subjects. That's a lot of over and unders, right? Don't go too high on the correlations because then you'll be screwed and you won't have enough participants. That's the summary. Okay, so this assumption setup won't change the whole semester, those 4 lines. So I'm just going to run those. Oh, except that's actually screening the subject number. It shouldn't matter. But we should probably exclude the subject number. Derp. Okay. Now you can screen categorical variables. We probably don't want to screen subject number. We'll see how big of a difference it makes, because I definitely did last night. So for normality, we're going to look at our histogram. Oh yeah, no difference at all. So don't screen subject numbers, but if you do, it probably won't make a difference. So that looks pretty normal. Yes, we have some people out here in the tails, but most of the data is between 2 and 2 and is centered over 0. If you aren't sure, try running those 4 lines again. Yeah, I'm getting approximately the same picture. But mostly, it's still between 2 and 2 and centered over 0. So you can run it a couple times if you're like, ooh, I don't know. But it's pretty normal. So this is the one I had here. This one's really pretty. This is actually not made up data, believe it or not. But so I don't know why it's that pretty. Bless you. Linearity is our QQ norm function. Looks okay. It's not good here or here. But the tails are always hard to predict because there's so few people in the tails of a distribution. So the tails will always be kind of your problem. If you look at the one I got last night, that's gross. But it's past 2. And that's 2 standard deviations out. So I'm kind of like, meh. So mostly I want this 2 and 2 rule is pretty common. Mostly the things between 2 and 2 should be pretty close to the line. So I'd say this one's okay. Maybe a little iffy. Like, what did I say here? I was wishy-washy. Alright, and then homogeneity. It's our same plot. Oh, that one looks better than what I got yesterday. Yeah. This way, mostly between 2 and 2. It's this way that's the problem. So you see how the spread is wider at the top than the bottom. That's going to be a sporicity problem for repeated measures. But, you know, like, it's not huge, but I'd say it's kind of problematic. If you want to see one that I would probably consider bad, the one I got yesterday was pretty bad. So the spread here is, it's 0 to 2 probably, but the 2 got cut off. And the spread here is 0 to 3. So that's not good. So I would say homogeneity is questionable. But the real thing to check for is sporicity. This is all the same stuff about sporicity. And then here's something important. I actually was like leading up to this Wednesday, and then listening to the lecture, I was like, I never told you a thing. So I made sure to put it in these notes. So something important. We talked about sporicity last week. as compound symmetry. So this is clearly not the marker I brought. That's crap. That's what that is. All right. If I have 3 or more levels, it's the I take 1 minus 2 and calculate the variance, right? And then 1 minus 3, and then 2 minus 3, and I get the variances for all of those. Are those equal? And then the correlations between them all. So 1 to 2 correlation, 1 to 3, that's a 3. 2 to 3. So sporicity checks if the differences in variances are equal and the correlations are equal. If you only have 2 levels, you will not get Mockley's. It won't even show up. You didn't do anything wrong. It just is not there. Why? Because there's only 2 levels. This seems like once you have this moment, you'll be like, oh, okay, that makes sense. But if you're not having that moment, right, I have nothing to compare to. I've calculated the difference in variance. What am I supposed to compare to? Magic? Correlation between 1 and 2. There's nothing to compare to. Because it's the subtraction of the levels. So it's kind of hard to compare correlations and variances to one thing. So you won't see Mockley's any today because we have a 2 by 2. So you have to have at least 3 levels before you'll get Mockley's. So for my homogeneity Mockley's problem, nah, whatever. Moving on. I have a lot of people, it'll be fine. So I forgot to say that last time. But if you're running a one-way repeated measures and you only have 2 levels, you're doing dependency and then, whatever. But this is where it gets people are like, what did I do wrong? I didn't get Mockley's. I'm like, nothing. It's a 2 by 2. So there's nothing to compare to. All right. All that aside. So in the script, I commented out the participant number because I already have one. So I'm not going to add another one. But so just kind of showing you, you gotta be flexible with your coding. So one problem people have is that if it deviates from the script at all, Rachel and I are usually miserable. So make sure you understand, what are you doing with each step, right? So that was my moment here, oh crap, I should have excluded the participant number. Since I have one already, I don't add another one. But we're going to switch from wide to long, so that's the reshape library. Make sure it's just regular reshape, don't do reshape 2. So here I am. I have my subject number, 4 columns. So what I did was the ID is subject, and then I have my 4 columns. Okay. Here's another thing that I haven't really told you guys about. So something new today. Is the names function. So all of these are really wonky to type, and if you have 100 columns, your life is pretty miserable sometimes because over here, I can do the little drop down and I can see all the column names, but I can't cut and paste them. / if you have a whole bunch, it cuts off. It just will only show you so many. So the names function will show you the column names in the order they're in. So I can cut and paste this here, stick it there, and put in commas. So I like the names function a lot because it also allows me to see what number a column is. So the little 1 out here next to subject, if you run names, that just means this is column 1. It also will let me cut and paste some really wacky column names. So I don't have to spell them right. Because that's often what your issue is, right? Something's not right because it's misspelled or you have a missing comma. So the names function. Okay. Wait, I wanted this open. Okay, so we're going to go from wide here to long. So run all 3 lines. And then, I'm going to rename the columns here. So subject, I'm calling the second column temp. You'll see why in a second. And then rating. So, long data, there we go. Here's the issue with these. This is why we did these first. This temp column has all 4 columns in it. So it just took the data and was like stack, 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 put it all in one giant column. But I have 2 IVs. So what I have to do, and this is fortunately, I guess, not too crazy because it's 157 rows stacked multiple times. If you want to ask someone about crazy stacking, talk to Becca over here. Where we had like items all wonky and they all had different numbers of rows, and I was like, I'm gonna cry.
It's okay, I cried about rows.
It was awful. So it could get worse. But what you have to do, if I scroll down some, I'm on 3 here. Don't overwrite this column, this temp column. We're going to use that to make sure we're doing this correctly. So create yourself new columns. And basically what I want to do is figure out the pattern of FSG. So here, looking at it here, in the wide data set, it goes low, high, low, high. Or you can look at it here, low. You scroll down for a while, you'll get to the part where it says high. Right. So what it did was it did low and then high, and then low and then high. Does everybody get what I'm saying? Because of the order I put them in. They went low, high, low, high. There's 157 rows. I got that from here. So 157 observations for each one of these. So what I'm going to do is create a new column that has 157 lows, then 157 highs, then another 157 lows, blah, blah, blah. For BSG, though, these will not be the same, or your ANOVA will not run. If I look at the way BSG is stacked, it's low, low, high, high. They shouldn't perfectly match, or they're the same column. And then it's the same, 157, 157, 7, 7. So I figured out the structure. So we're going to use the repeat function. So this is under fix the double IV issue. So what the repeat function does is it will repeat the first thing. So I had it low, high, low, high. The second number is how many times. So it's going to repeat the word low 157 times. Just highlight that real quick. So the repeat function is really great. It repeats a number or a letter or anything you want X number of times. So I would get 157 lows. Since I figured this out, I want to repeat this 157 times and then repeat this 157 times, etc. So this is almost if you had to hand code it in Excel. This is much faster. The worst trouble people have is figuring out this part. What's the order of them? And so the way to do that is look at what order you put them in the melt part. Okay. So I'm going to make myself 2 new columns. That's much easier than GL, yeah? Yeah? Okay. Now for the second one for BSG, because it was 157 twice, I just added them together. Now, let's see what that looks like. So now when I look at long data, I can't point with the mouse here, this one's low and this one's low, and that matches what's in my temp column. So this is why don't overwrite the column you have, because that's the one that where you're making sure that coding worked correctly. So this should be low for both of them. If you scroll down to at least past 157. FSG switched to high, is that right? Yeah, high, low, high, low. So all we've done is taken that one column and break it into the 2. But always don't overwrite the column so you can check to make sure. So that's why I said be sure you check out the results. So make sure at one of the places it's supposed to switch, it actually switches. Questions on that thought? Not until you try one, probably. But write this out for yourself and make sure they're not the same. because otherwise this next ANOVA part won't run. Alright. Now, right now, the variables are characters. So if I look at long data, it says FSGCHR. That stands for character. I would need it to be a factor. You don't need it to be a factor for the ANOVA part to run, although it will be happier if you do. But when you get to the graph, it will basically... If ggplot, I can imagine it barfing. That's what it does when it's not factored. It just gives you an error. So we're going to use that factor command. We've gone over that a couple times. Notice that my labels are the same because they already had the right typing for them, and I made them proper case, so once I got to the graph, I didn't have to do anything with it. Right. And now it's a factor here. So that'll help. So honestly, the setup for this takes longer than the actual ANOVA, which I feel like is always true. Okay, so what is new? Oh, here's the new piece. I'm looking at the easy ANOVA part. Here's what's new, right here. Oh, I can't point that high. Here. I don't understand this coding. I don't know why it's just like something, comma, something, or list, because tapply uses list, or C, or any of those other functions that we've done 100 times, but instead it's just a dot. I didn't write it. So you do within equals dot, and then it's got the parentheses, and it needs to be all the variable names. So you can put in 10. I don't recommend doing 10, but this is how you enter more than one. So I've got my data set, long data. My within subject's ID is my participant number. Within here is the two IVs, DVs rating, type still equals 3. So that's the new piece right here. When we do double between, it's the same. It looks the same. It just says between equals. All right, I'm gonna run my ANOVA. Yeah, and over here. So you notice no Mockleys. Right, so we only have 2 levels, so it won't give it to me at all. So I put a little note here. This right here is the same as the last class. I just left it in. But it has this new, like, if levels are greater than 2. All right, so are they significant? Yes. Yay, look at this p-value. Negative 46 and 68e. That's pretty intense. So they are significant with the helpful little star. We've got medium to small effect sizes. My interaction is significant, which is what I wanted. Woo! But I've got 3 of them. Kind of told you why already we have 3, but later in life, if you're like, wait, why are there 3? Yay, I have the explanation. Okay. So you have 1 for each IV and 1 for the interactions, and you interpret them all separately. And I have no idea what the remember is about. Remember.
What each of the little abbreviations stand for?
Nope, don't know. It was a thought. I think remember. Oh, I remember now. No, I think I got distracted. If the interaction is significant, only do post hocs for the interaction. I think that's where I was going with that. See, but I also have it down here, so it's in here like 4 times. So at one point you'll get it. Right. You still report the main effects as being significant. So it's not like you just leave it out if you're going to do the interaction. Well, the interaction is significant, forget the rest. You still report the main effects, you just don't run post hoc on them. Okay, all this is the same, so here's my example write-up. I just did APA because really AMA is not that different. So I've got really big effect for FSG. That was the purpose of the experiment. They're supposed to rate the low ones low and the high ones high, so I don't really care. I have an effect of BSG, so with a high backwards relationship, people are rating them higher. If you look at the means, okay, not a big shock, but I'm really interested in this interaction. What makes that combination, what happens to their ratings? So, what I'm going to do is look at my means. And we have been using this list function all year and never have really needed it until now. So 2 months of prep for this. Right? Essentially, when you have more than one IV, you put both of them in the list function. So that's what the list actually has been for this whole time. That will allow me to get my mean, standard deviations, and n for the interaction. The real problem, though, and this is specific to this example, is that since they're both low and high, it's not obvious which one is which. Yeah, I had to go back and relabel them to match. So I should have done F low and F high. But the first variable goes down, the second variable goes across. So it looks like these. Okay, FSG low here, BSG across. So what's happening? If I look at my means, I make a graph. I got 50 points for low, low. 56, right? That's FSG's go back. Yeah. 56 points here. And then 64, 78. Not to scale. So if I look just at FSG low, this is BSG low and high. There's about 6 points difference. If I look at high forward strength, there's 13 points difference, 13, 14 points difference. So the interaction is caused by the fact that there's only 6 points different here and there's 14 points different here. So yes, they have the same pattern. Low is lower than high, or high is higher than low. Either way. Okay. The reason that the interaction is significant is that they're not the same. This is what I mean about patterns. If they were both 6 points difference, there would be no interaction. Because then it would look like this. So if there was no difference in the pattern of the bars, that's like a really goofy diagram, but they would have parallel lines. Now, so I have my means. If I wanted just forward strength means only, I would just take it out, backwards F strength out of the list. So the main effect for forward strength was significant because the low ones they're rating at 53 and the high ones are rating at 71. Okay. And then backward strength, the low ones are at 57 and the high ones are at 67. So that's why those two are significant. But there's only 2 levels, so there's no test. So I would just look at the means. But I don't care about that. I want to know about the interaction. Tell me what happened. Down or across. I feel like I have these phrases I end up saying a zillion times. And down or across is definitely one of them. So this is what I have drawn in here. I tried to do. So what I mean is I could compare across and do FSG low where BSG is low versus high. And then do FSG high only, FSG low versus high. So that would be comparing here across. Or I could compare down. So for only BSG low, only BSG high, and do FSG low versus high, FSG low versus high. Pick one, down or across, not and. Okay, so otherwise you're doing more type 1 error problems. So we would pick across or down, not both. The direction will depend on the hypothesis or whichever weighs faster. Legit, that's one of the rules. So if you have a 2x3, so let's say I decided that I really needed to see this better, so I did low, medium, and high. If I went down, it's only 3 tests. So 1, 2, 3. That's pairwise, 2 at a time. If I went across, it'd be 1, 2, 3, 1, 2, 3. It'd be 6 tests. So go the laziest way, so the way with the least number of tests, or with the hypothesis. So hypothesis first, lazy second. All right, so what I did in this particular example, based on the hypothesis, was I split on FSG, because the low FSG should be lower than high. I don't care about it this way, because that's not answering my question. My question is, why, with back restraint, is it causing people to up their ratings? So I split across here, which is what I have written in my little table. So what does that mean? I can't just run pairwise T, because it doesn't quite, it doesn't really allow you to say only when FSG equals this. There are some functions that let you do that, but this is not one of them. And I can't run it on the temp column, because then that'll have 4 means, and it'll run every pair to every other pair, and that's too many. So what I have to do, just practically, is split the data set. So that's where I have this split function. So this is the subset function we have been using all semester for outliers and missing data, now to split. Now here's something you want to do when you're doing this. Long data has 628 observations. So whatever you do to split it should still add up to 628. So I'm going to use subset long data where the forward strength column equals. I don't know if you want to put like a note here to yourself, or a thing, or a star, or a sticky note, or tattoo. Don't do 1 equals. Will not work. I cannot tell you how many times that's the problem. 2 equals. Equals equals low, equals equals high. So watch what happens if you do 1. It doesn't give you an error. It doesn't tell you, hey, stupid, that didn't work. But if I look at FSG low, it still has 628 columns, or rows, which means it didn't do anything. If I run it with 2 equals, now it only has 314. If I run the second one, my BSG, or my FSG high one now has 314. That adds up to 628. It looks like it worked okay. So the short answer is double equals. Make sure they add up correctly. All right. So I filled in all my numbers here, but on this table, one of these should stay constant. So my FSG low, I split them in half. So 4 only low, 4 only high. This is where the split comes in. So this should stay the same, and then I've got low versus high here. So that first one isn't about, it's BSG low versus high, but only when FSG is low. So sort of, I guess you can think about politics since it's politics season, right? Debates right now are only Republican and only Democrat. So-and-so versus so-and-so. Right? Same idea. Only when it's low, only when it's high. Compare these two little things. So I just put in my mean, standard deviations, and n. You will make one of these tables on the homework. That just helps you with effect size. Okay. We're still doing dependency and repeated measure because it's repeated measures. And Bonferroni because it's easy. But you'll notice we'll only get 1 test. Because it's low versus high. That's it. End of story. Just 1. And it's significant. And then the same thing for the other one. Also significant. You'll notice that they're exactly the same. That's because it's ran out of significant digits. They're very different. But I can tell that I did the right thing because this says FSG low here. And this says FSG high. So if you're like me and you like to cut and paste code a lot, make sure you change. They're not running the exact same test. That's the only thing you need to check. So the data set name has changed here. All right, it's significant. Woo! What does that mean? high BSGs are rated higher than low BSGs. Okay, that shouldn't be. That's the point of this experiment, because backward strength shouldn't matter. But it does, clearly. But this does not imply an interaction. It's the same pattern, high is higher than low. Sometimes they flip, where it makes like high is higher and the other one will be low is higher. So that's a pretty common interaction, is where they switch sides. Or one of them is significant and the other one isn't. That's also an interaction. This, to me, is the harder thing to interpret, when they're the same pattern. Like, okay, so what makes it an interaction? Because if it's the same pattern, there's no interaction. And that's when, like, effect size on its glorious unicorn comes gallivanting in. It's really hot. I'm starting to get a little loopy. And I love effect size, but here's why. It's because that will explain to me what actually happened. So it's still dependency averages. I took that effect size document and loaded it already. But if you have not loaded it, make sure you do that. So, open F size, run the whole thing. You can also use moat if you like moat better. So I filled in all my means and standard deviations from my table that I made, so that's why I make a table. The first one is a medium effect size, so about 0.5. And the second one is triple the size, so it's 1.5. So the interaction is caused by them being the same pattern, but one of them is a medium difference and one of them is a very large difference. So the pattern's the same, but the size of the pattern is different. So one of them is triple the effect size of the other one. Now, this isn't in here anywhere, but every once in a while, something will happen where you'll get a significant F test and then none of the post hocs are significant. I literally got this email the other day. Why? Well, the F test just tells you if any of the means are different. It doesn't mean that the direction that you pick to cross or down is going to be the significant one. So sometimes what happens is you'll pick to go across, but the difference, statistically significant difference, is down. Or because you're using a correction, you will, and it was close, so if your ANOVA is like 0.04, you correct that, it's probably going to be gone. That does happen. It's pretty rare, but it does happen. You didn't do anything wrong. It's just maybe not quite the pattern you wanted. All right. Last but very much not least, ggplot. So I'm going to run this giant block of theme coding. It doesn't change. I'm cutting and pasting it from document to document, just so I don't have to remember how to make the graph pretty. But there is something new. So if you want to highlight the new part, it's this for fill. I had a serious moment yesterday. I was like, fill versus color. God, do I remember how this works? Okay. So we're going to use fill. What does fill mean? Fill colors in the bars. Okay. So I've got my aesthetic, AES, my X column, my X axis, then my Y axis. Fill is the legend. Okay. So this is going to be your X axis. Right, so it'll be the first one. Here's Y axis. Everything in fill is out here in the legend. Because we've got two IVs, that's an in. So it's filling in what color the bars are. Make sure your variables are factored. This is where it won't run if you didn't factor. And then we'll run this, and then just the word bar graph. We should get a barely blank bar graph with FSG on the bottom. There's no legend at the moment because it doesn't know what to do with the legend. So I got my blank graph. Here's something else new. Did I fix it? Yeah, here. It doesn't look like it's changed much, but what we've done is taken out fill and color. So you can't, on the last repeated measures graph we had here under stat summary, it said geom equals bar, and then it had fill equals white, color equals black, something like that. We took that out because if you have two fills, it gets confused. So we move the fill to somewhere else. The rest of this stayed the same. Okay. So if I run it from bar graph through the stat summary, I will get, don't ask me why it's red and green, but the default color is red and green. Teal, red and teal. It looks green to me. Oh, it looks blue on this screen. It's totally green on this screen.
It does.
It's like aqua teal. Anyway, okay, yeah, red and blue on this. Anyway, but look, we got a legend. This legend is such a pain in the butt. We'll get to that in a second. All right. If I put my theme coding on it, that helps with the coloring. Okay. So when on the homework it says be sure your graph is cleaned up, aka no black, gray backgrounds and stuff, that's the theme part. So I've really cleared out the gray background, and without fixing anything else, you can see the interaction. These two bars are closer together than these two bars. That's why an interaction. Next thing I want to do is clean up X and Y. So we did that last time, X lab and Y lab. So now, readable, much better. I've already capitalized low and high in my factor command, so I don't have to do scale X discrete. But this stupid PSG over here. Right, so the legend. This took us forever last semester to figure out, but the legend problem, they're laughing because we had a lot of problems with this, at least I have figured it out at this point in life, right? Is scale fill manual. Okay, this is at the bottom of page 21 in the notes. So we used the word fill in the first line. It said fill equals this. So the solution is scale fill manual. So the fill and the fill have to match. When we get to scatter plots, it'll be color. And so you have to have fill and color matched together. So the scale fill manual, because we use the fill command. The manual part, instead of discrete, allows us to change the colors. So if we did scale fill discrete, like scale X discrete, you see what's going on? Scale X discrete works on X and manual. But this is how you change the labels here. We did that last week. This is scale fill. You can do discrete, we're not going to. You can also do manual. I had an existential crisis yesterday. It was manual with an A or an E. I was like, oh, it's so late. But the word fill matches what it's changing. Scale X discrete changes Y. Scale Y discrete changes Y. I said that wrong a minute ago. Scale X changes X. Scale Y changes Y. Why manual? Because then I can change the colors. You can play with it and make them pink, purple, green if you'd like. But the name part controls this section here. Values is what colors you want. And if you wanted to fix the labels, it's still labels. My labels are okay. So I'm going to run everything. Alright, that changed it to gray. That was intense. You can make them, you can play around with what color names it'll accept. Don't do white, and here's why you don't want to do white. Because then there's no bar. Because we haven't done the outline. But it will accept all kinds of fun color names. It is in crayons, but not in here. And then if you've ever done, oh, it didn't like teal. If you've ever done any HTML coding, it will take RGB codes and hex codes. So if you do color picker hex, you can pick a color. And so it'll take these little hex codes too. So I could, the university uses very specific combination of hex codes. I could do that as well. I think that should work. Oops, fine. Again with the quotes. Oh wait, does it need the ampersand? It might need the ampersand. So if you're going to use hex codes, I think you have to use the ampersand. The ampersand is the squiggly one. The hashtag, pound symbol, there it goes. Pink. Right. Number sign. Really hot. Okay, so that's how you can change the colors on it. For the homework on these, you just have to prove to me that you can make the graph look pretty. So you could make it black and gray if you wanted, but if you want to make it fun colors, it's fine. As long as it's clear that you cleaned it up. I know how to work this code, and I made it my favorite colors. Alright. Then, in the notes, it's got an example of the write-up. Oops. I did that, so take that line out. Okay. So